Many cyber-physical systems are sampling from the real world in real time, and then they're making a control decision based on those samples. But what happens if it takes too long to make a control decision? Typically, this becomes a big problem if you're trying to avoid some obstacle in the real world, that if you can't make a decision fast enough, you end up making the wrong decision and not being able to avoid an obstacle like a driver normally would. When an obstacle is not moving, we can typically just drive in a straight line. So the problem becomes when we need to be able to move around some obstacle with a very small margin of error. In this case, we typically use what we consider to be a very accurate model. The downside of using this approach is that it takes longer to compute the control inputs that we need for our real-time system. Using a less accurate model gives us faster results, but the downside is that the results are probably not as accurate as we need them to be. This unfortunately presents us with competing goals, that we need to be fast, but we also need to be accurate. The goal of this research, therefore, is to consider this time that it takes for us to make some of these computations as an integral part of what it is that we're trying to do, so that we can switch between multiple models based on which one is likely to be the most accurate compared to the kind of accuracy that we need. This enables us to make decisions in real time based on two different and very different computationally time-dependent models. In order to do this, we need to know how inaccurate each model is, and we also need to know how long it takes to make decisions with each of these models based on their computation time. With these kinds of data, we can then make decisions that allow us to avoid obstacles and even avoid a field of obstacles by switching between the two different models. With a firm understanding for how this works with ground vehicles, we're now ready to expand our research and examine how it will be applied to aerial vehicles. Our research team has in-person meetings as well as regular Skype meetings in order to make sure that we're covering all of the tasks that we've laid out for the research agenda. This research agenda is broad and has multiple years of effort that are required, including effort on both ground vehicles and aerial vehicles in order to understand the theory and the applications that it might have, so that we can take what we've learned on the whiteboard and apply it directly to the kinds of applications that will improve the state of the art.
In the Hybrid Systems Lab, we use a motion capture system and nano quadrotors to test our solutions based on what we have found in our simulations and theory. Our motion capture system uses 8 Flex 13 cameras, a Crazyflie 2.0 quadrotor, and the Motive motion capture software to gather data about our system of interest. Here we are demonstrating the results from our research on set-based predictive control for collision detection and evasion. As the projectile is thrown towards the quadrotor, our algorithm predicts the trajectory based on standard projectile dynamics and determines whether or not there will be a collision with the quadrotor. If the algorithm detects a collision, a set of linear trajectories are planned, and the optimal trajectory is chosen based on minimizing the distance to our defined target. In these experiments, the quadrotor is initially hovering at the target, so the observed behavior of the quadrotor is that it moves away from the target to avoid any collisions and then returns back to the target when safe. In this next experiment, we decrease the radius of the safety set for the quadrotor to 0.4 meters. A smaller radius means we might compromise safety for efficiency. We can see this sort of trade-off occurring between the first experiment and this experiment when we decrease the safety radius from 0.5 meters to 0.4 meters. Here we show an aspect of our research that leaves room for future improvements. We can see in this video that the quadrotor is hit by the projectile, but only after a bounce occurs. Ideally, we should be able to model the projectile with hybrid dynamics so we can accurately predict its motion after a bounce occurs.
We are currently moving forward in the implementation of computationally aware model predictive control. By using a set-based approach to account for uncertainty effects in the sensors of autonomous vehicles, we can have more robust controllers. Applications of this research will lead to improving obstacle avoidance for pedestrian crossing under urban traffic conditions.
In the following example, we demonstrate obstacle avoidance problem using a set-based predictive controller. The autonomous vehicle, the RC car, is shown navigating to the target while avoiding a stationary obstacle. Our simulations and experiments show the effectiveness of our proposed algorithm on a real-time platform. Challenges arising from computational complexities, delays, and unmodeled dynamics could pose a significant performance degradation. Nevertheless, the vehicle was able to successfully achieve the obstacle avoidance task while converging to the neighborhood of the target.